Hello everybody, and welcome back. So we've already talked about conduction, and we've seen what the governing law and the equation for conduction is. Now we're going to talk about the second mode of heat transfer, and which is convection. So as I've mentioned earlier, convection occurs when you have a moving fluid. Let's say you have a moving fluid that's moving over a stationary solid surface, for example, and you have that solid surface is, let's say, hotter or has a different temperature than the actual fluid that's moving over it. What you're going to see happen is, so if that surface is hotter, you're going to have heat exchange, so heat flow from the surface and into the moving fluid. Now, an example of that could be as simple as if you have something that's hot, let's say a hot surface, a hot rod, and you decide to put a fan in front of it to blow air into the hot surface so that you can cool it down. So what happens is that you have the air removes some heat away from the surface, and therefore you can start cooling the hot surface. Now, how do you compute the heat exchange? How do you quantify that? And this is what we're going to try to do together right now. So before jumping into the equations and all of that, let's first make sure we agree on the definition, and on a high level, I want to explain what occurs. So convection is a mode of heat energy transfer that occurs between a surface and a moving fluid when there is a temperature difference. If there is no temperature difference between the stationary surface and the fluid that's moving over it, then essentially there is no heat exchange. And so there is no convection heat transfer occurring. Now, when there is a temperature difference between the stationary solid surface and, let's say, the fluid that's moving over it, then there are two simultaneous mechanisms that are occurring at the same time. And the combined effect of these two mechanisms is what we call convection. So the first mechanism is very close to the wall where the fluid is traveling, you have a microscopic energy transport due to the random molecular motion that occurs just above the solid surface. And this is just like with conduction. Now, however, just above that surface, above where the microscopic energy transport dominates, you have the bulk fluid motion. And that is where you have the macroscopic energy transport due to the bulk fluid motion. So you have these two phenomena occurring at the same time. One closer to the surface where you have the molecular random motion dominating the energy transport. And so there is an element of conduction of convection in of itself. And just above that, you have a region where you have bulk fluid motion occurring, whereby you have energy transport due to that bulk motion. And again, the combined effect of these two mechanisms is what we call convection. Now, let me explain that with this example over here. So you might be familiar with this drawing because whenever we talk about convection, there's usually some kind of analogy that we try to describe what's going on through. So let's assume you have fluid flowing, and these arrows just represent the velocity of the fluid that is flowing over this flat plate. So before it reaches this flat plate, you could see that the velocity of the fluid, let's say this is air, or let's say this is water, liquid, you have the velocity of it is constant, and you have the temperature of it, which is T infinity. Let's say that if that is air or liquid, it is constant. Let's say it's at room temperature, just for the sake of this conversation. And what happens is, as the fluid approaches the leading edge of the plate, so as the fluid approaches the beginning of this flat plate, we said that it already has a uniform free stream velocity of U infinity, and also it has a uniform temperature all along that fluid of T infinity, let's say it's ambient temperature. And so upon contacting the plate surface, so as soon as it touches the plate surface, the fluid velocity at the wall, so the fluid velocity closer to the wall, just above the flat plate, would become zero, because we know from fluid mechanics there is something called the no-slip condition. And the no-slip condition means that the fluid just in contact with the wall would have a velocity of zero. And therefore you get a velocity boundary layer that begins to develop from the wall to the bulk of the fluid, which is some distance away of the flat surface. Now, if a temperature difference exists between the plate and the fluid, then you'll have a thermal boundary layer that also begins to develop at this leading edge. So if there's a heat difference, you will not just have the velocity boundary layer that normally would occur, but you also on top of that have a thermal boundary layer that also begins to develop from the leading edge. Now, if the plate is hotter than the fluid, then heat is transferred from the surface to the fluid by molecular diffusion near the wall, and this is the microscopic element. And then further away from the wall, you have the bulk fluid motion carries the heated fluid downstream along the plate, and that is the macroscopic element, and therefore you have what we call convection heat transfer. I'm going to go into more detail about the boundary layer theory so that you can understand what exactly is happening as you travel along the solid surface. But for now, I just wanted to give you a high-level overview of what is convection, what is happening, and give you an idea that while a velocity boundary layer develops, we also have something that we call a thermal boundary layer that also develops at the leading edge of the solid surface. Okay, so now we know the definition. Let's actually see what we can use to quantify, to express this.